My name is Anna Steffi. I'm part of Group 19.
My name is Zach Barnett, and I'm part of Group 19.
I'm Doling Jia in Group 19.
Oh, I was reading. I'm Alana Jadwalis. I'm in Group 19.
And this is going to be our video discussion for recitation 10. And I think we just go through the questions on this one. Yeah. Awesome. So this is all about a bicycle wheel with a rim of mass m and an axle of mass lowercase m, and it's on a horizontal surface. Starts at time 0 at rest. We got to define the speed. Did anyone want to talk about how they found speed first?
Yeah, so for me, I think we all pretty much agree on it. Use the energy principle, so the change in internal energy, set that equal to work. And we just have the change in translational energy, kinetic energy, plus the rotational kinetic energy, and then plus potential, but potential of the situation would be 0, and work through that, plug everything in, and it comes out pretty much to what we all agreed on as the answer. We all pretty much the same thing.
Yeah, I see. Okay, for 2, it says determine the magnitude of the friction force on the surface on which the wheel rolls exerts on the wheel while you are pushing it. I see, Alana, your work looks really similar. Yeah, I think we have the same thing. I just simplified it to death. But it was that my idea was, again, just using a point particle system, and force multiplied by distance is equal to this, and I just found the hidden frictional force. Did anyone use any other different method than this?
No, I had the same thing with Alana, so I didn't have the same simplified answer you did, but I did pretty much have the exact answer she had as well, but it's the same thing. So
Yeah, the idea is the same.
So now for recitation 3, if in fact the bicycle wheel was a sphere, would it experience the same rolling friction as the wheel? Did anybody have any reasoning? Gia, what did you think?
Yeah, I would say no, because like the moment of inertia will be different for a sphere instead of the like disc or yeah.
Yeah, I agree. I thought that it would be less than in the case of the sphere, because we could set up these, working with these different moment of inertias that you brought up, Gia. And if you would solve for frictional force for both of them, you would find that it's less in the case of the sphere. And then a string is wrapped around a uniform disk of mass m and radius r. Attached to the disk are 4 low mass rods of radius b, each with a small mass m at the end, showed below. When you pull the string with a constant force of F, at the instant when the center of the disk has moved a distance of d at an additional length of w, the string has unwound off the disk. At this instant, what is the speed? Yeah, this was really simple. This was just the point particle system, summing all the mass, force times distance when the force is just where the distance is just in relation to the exact force that it was acted through, really similar to part 1 of this. And I see everyone agrees. Part 2, at this instant, what is the angular speed? All right. Does anyone want to talk about how they got this?
I mean, yeah, it's not too much different than anything else we've done, to be completely honest. So it's the same energy principle kind of thing. Just this time with including W and including angular rotation as well. Like everything in me now, it simplifies down to we all pretty much have the exact same thing. We have it written out and simplified differently, but it's still the exact same instant.
Yeah, I think as long as you know the identities and where this momentum of this moment came from, I think that, yeah, we are just all in agreement. I think they were actually meant to be very similar to show that the process by which you solve these problems is actually pretty similar.
Yeah.
Yes.
All right, are we all good, or is there any questions?
I think it's
Good.
good.
All right.
Yeah, good.
thanks.